Hi everyone. Today I want to do a really quick, hopefully a quick walkthrough on one of the questions on assignment 5. I hope that this one isn't too tough. It's mostly, there's a lot of conceptual questions on here. It is tricky. Try to use the slides when you can to kind of help you out. I'll try to help you out on some of these too. But for one thing, I know I'm getting a couple questions here about the finite correction factor for the sample mean and how you might proceed with that in the future. So I'm going to go ahead and do question 3 here. Just kind of walk us through it, and then I'll finish that on your template. For your Excel quiz, I didn't walk through it in the video, so it's actually okay if you don't want to complete that part. You can just leave it blank, that's fine. No penalties there. You do walk through it on the sample proportion, which is fine, but I did want to show it to you because I think on your exam there's going to be a question about that, and so to give you some just a little bit of help with that. So let's do question 3 here. First two are just kind of conceptual. Here we're given the population mean income for recent graduates is about $54,000 and the population standard deviation is $14,000. We'll assume a random sample of 125 recent grads, and then we'll answer our question. This is just to kind of give us some information about the sampling distribution. So I'll go back here to my template. I haven't finished it or completed it yet, anything like that, but I'll start walking through here, just kind of plugging some values in, trying to remember. So 54,000 and 14,000. All right, and then the sample size was 125,000, I think, or 125. That's would be quite a bit. All right, 125 for our sample size. If you remember the properties, so the sampling distribution is actually kind of a tricky idea. We're trying to get an idea of what the sample means would look like if you took a bunch of samples, right? So what does that distribution look like if you took a bunch of samples and calculated the sample mean from that? So here we know on average, this is one of the neat properties of this, is that on average, the expected value of the sample mean is equal to the population mean. That's why we like to use sample means. We think they're kind of a good estimate, is because if you took the average of those, they would give you a really good, a really pretty strong estimate that we have here. The standard deviation of the sample mean, we said that this is kind of like it's the population standard deviation divided by the square root of n. So it's going to tell you something about the variability in that sample mean, how much variation around there. If you take a bigger sample, that variability is declining. That's why we're divided by the square root of n. All right, so we've got our two results that we have right here, our standard deviation of the sample mean. And now you can walk through this too. I'm sure you've done this already. We said, this is the cool part, is that, again, it doesn't really matter what the underlying distribution of the random variable is, but the sample means, those estimates are actually normally distributed if it meets that central limit criteria. So we can plug in values for the sample mean here and get some probabilities that we're looking for. All right, so let's put our sample mean value in here. These would be the different values for our next part of the question. So let's see if I go back. We've got the expected value of the sample mean. So on average, we talked about that. It should be the true population mean. We've got the standard deviation. This is the variability around the sample mean. It's really just saying, like, if you go back and we said a lot of our observations, like almost 2/3 of our observations, will be within plus or minus 1 standard deviation of the mean. If we're looking at incomes here, it means that within plus or minus about $1,250, we're going to find it's very likely we'll have the true population mean, right? That it's going to be included inside this interval. And so that's great. If I could get an estimate, if I knew I was going to take a sample and that it's really likely that the true population mean is going to be within plus or minus $1,200, that's a good estimate. That's precise, I guess we would say, something like that. So as you kind of go through, that's what you're thinking about here. Now we got to do some probability questions. what's the probability that sample mean will be less than 52,000? So that'll be my first value that I'm going to plug in here. All right, and I think it was less than 52,000 we were talking about, right? I need to do these. I haven't done these myself yet, but this is just the norm.dist function that we have here to get these probabilities. My x value, you've done this hopefully already, so it's just going to automatically fill in. I hope for you you've done this so that you can check your result right here too. All right, and then true. I went through that too fast, just so you know what we're doing here too, so you can see it. You're looking for the x value, that was the sample mean. Then the mean of our distribution right here is the expected value of the sample mean, and then it's the standard deviation. The sample mean would be our standard deviation for this particular case. It's an easy one to get confused on. And then true for the cumulative part, and we can get our result here. All right, now this kind of makes sense. We don't do so much of the math here, I suppose, but this should kind of make sense since we're below the mean, and we are about $2,000 shy. So we're getting further away since our standard deviation is about $1,250. This kind of makes sense that it should be less than or equal to 52,000 is going to be a relatively small probability, which is what we're getting right here. Okay, and then to get the other side, remember we're going to use that complementary relationship. We can just do 1 minus. If you're looking for bigger, that's what you would get there. Okay, all right, so our answer in this case would be about 5.5%. And to put this one in perspective, there's about a 5.5% chance, given the values that we've been working with, that your sample mean from your sample would be less than $52,000. So we're getting further away from we know what that true population mean is of $54,000. But there's only a 5.5% chance that you would get a sample mean below that value. That's not very much, right? So that's kind of neat. It's saying, okay, well, there's a low chance. It's not impossible, but it's kind of small chance that you would get a value in there. Okay. All right, our next one, let's take a look. Oops. How about greater than 55,000? We're just going to change our value here for whatever our sample mean. What's the chance that we get a value sample mean from our sample above 55,000? We're looking for the greater than side right here. So we can see that's about 21% in that case. So a 21% chance. A little closer, only $1,000 above the sample mean, so just a little bit bigger. And we've got, okay. All right, then our last question here, we can go ahead and take a look at it. What's the upper and lower bounds? We put 5% of the distribution, so we'll let alpha be 0.05. Again, I hope you've taken a look at this already. If you've done your template, but you can use this as a way to check. We can get our z-score by using norm.s.inv. I think the previous video does walk you through this part. Again, we're just trying to figure out, using the standard normal, right, what would that value be on that, from -3 to 3, where would it be where it puts 5% in those tails? This gets some weird math going, right? So so we can make sure we get a positive z value, we'll do 1 minus whatever that alpha is, so that we could change it in the future, divided by 2. That's why we set it up like this, so that value can change. And so we know that's a value of 1.96. We can get our upper values, again, following the same pattern of the video, the same structure. It's essentially what we're looking for here to get that upper bound. The sample mean or the population mean, either one in this case is okay. It ends up being the same value plus then the z value multiplied by the standard deviation of the sample mean should give us that upper bound that we have here. And then the same thing, we're going to use the same values. Essentially, we're just going to subtract to get the lower bound minus that z value multiplied by the standard deviation of the sample mean. And there's our upper and lower bounds. Okay, So we've got upper lower bounds. We can describe those. We can see here in this case, that's like 5%. So these are kind of defining these boundaries here, where we're looking for those sample means. This is where we didn't get to this the finite population correction factor. Again, you don't have to use this for your homework. There's not a problem that requires you to use this, but we could do this again because there's a possibility where you might need this in the future. All right, so let's think here, and let's just suppose you get one where we need to do this. And the reasoning is, if your sample is really big relative to the size of the overall population, you run into this problem where you're gonna like possibly oversample a little bit, and so that's what the finite correction factor is trying to prevent. And let's see if we can do this one right here. Now, I was trying to figure out how to best explain this. I think this will be kind of cool. So if we take a look at this particular question and look at the standard deviation of the sample mean, what if we said if you're sampling more than 5% of the population is a problem and you need to use the correction. But what if you're not? Like, what if you're sampling a really, really small part? Like, what happens if you use this? And the cool thing about it is that it should approximately be like the real standard deviation, or the sample standard deviation value that we have here. So we can kind of approximate that here by saying this. There's about 4 million students who graduate college every year. So if we use 4 million here, so we could put 4 million as our total population. If we think of roughly 4 million students are going to graduate and our sample size is 125, we know this is going to be a really small percentage of the population. Okay, so if we're going to use our standard deviation, our correction factor here, we don't need to use it, but we can see what would happen if we did use it in this case. All right, and then I'll show you, what would happen if we were sampling too much. Okay. All right, so the standard deviation, the correction that we'll have here, that we'll use, if you go back, it's pretty much just the standard deviation of the sample mean, the standard error, times by the square root of big N minus little n, divided by n minus 1. All right, so let's give this one a try and see what it looks like. Okay, so I'll let you go back through and check the slides to see what this looks like, but you'll notice something I think kind of cool here. Because our sample size is so low, actually, the correction factor shouldn't really do much to our standard deviation. And because it's actually so small in this particular case, really that standard deviation should be the same. All right, so here's how we're going to do it. Equals, I'll make this just a tiny bit bigger. All right, equals square root of big N. Oh, I gotta be careful myself here. We're gonna need some extra parentheses just to make sure everything comes out right. Big N minus little n is divided by big N minus 1. Now you might notice this. Because our big N is so big, really that ratio is going to be really close to 1. So if you notice that, because essentially because the sample size is actually really, really, really small. So this isn't going to really do much, and that's because we don't have to worry about this problem of taking too large of a sample. Okay, so once we have this, that's all we need there. I'll scroll up. I'm going to use the standard deviation of the sample mean. That's how we would correct it in this case that we have here. We can hit enter, clean it up a few places, and you'll notice it's very, very close, very close to what we had up here. So not much of a difference, and that's because we're staying within that criteria that we kind of know about. Okay. All right. Let's do this really quick just to see. I think this would be interesting. What if not very many people graduated from college every year, and we said like we take it down to like 250 or 300 or something like that? We need to make this correction in this case. You can see the difference that we would use. So if that population was actually quite a bit, smaller, the overall population size, we sample 50%. Here's what our standard deviation is that we would want to use in this particular case. Okay, we could even change this to 500, I think. So we're still taking 25% of the population. And we're still going to make a little bit of a correction here from the 1200, just assuming that we had a normal sample. Okay. All right. Again, you don't have to do this. There are really good questions about like what numbers do I use. A lot of times it's just kind of playing around, trying some stuff out. You don't need this for your quiz. I won't take points off if it's not there. You don't need it for your assignment this week. It's not necessary. But there is going to be a question on the exam that you could just do on pencil and paper, but you have it here too now as a demonstration. So let me know if you have any questions, and good luck.